The recorder malfunctioned once more. Fortunately, it stopped at a good place. It's at least doing that to me, so let's just finish up what I had on the last clip and then move on. Okay, so what good does this do us? Let's suppose that we have some function f of t whose Laplace transform is big F of s. In other words, f of t, big F of s form a Laplace transform pair. Big F of s is the integral from negative infinity to infinity of little f of t times e to the negative st dt. Question is, what is the Laplace transform of the derivative of this function f? We're going to be able to express the Laplace transform of the derivative in terms of property of the function f and the Laplace transform of that function f. So, let's write down the definition. Okay, the definition is the Laplace transform of f of t is the integral from 0 to infinity of, I don't know if I said prime. Laplace transform of f prime of t is the integral from 0 to infinity of f prime of t times e to the negative st dt. So what do we do with this? Now you might have read ahead here, might have given it away, but if we look at this thing without knowing where we're going, what do you generally do when you have something multiplied by an exponential function and you're trying to integrate it? It's easy to take the derivative or to integrate an exponential function if we can simplify the form of this thing by taking the derivative or integrating this function, then integration by parts will simplify our integral. It turns out in this case that the derivative of f of t is f prime of t is f double prime of t, and that isn't particularly helpful, but if we integrate f prime of t, we get back to f of t. So we're going to do an integration by parts, and what we're going to do is we're going to let our dv equal our f prime of t dt, and our v, that'll make our v equal to f of t because an antiderivative of f prime is f. And u will be the rest of it, which is just e to the negative st, and the du is just negative s e to the negative st, very simple derivative. Now integration by parts, remember, says u dv equals uv minus the integral of v du, and I see my camera kind of flickering, so I'm a little bit leery here. Let's hope this works. Okay, so if we follow the process through, we get the uv is just our e to the negative st times f of t. Our integral goes from 0 to infinity, so this will be evaluated from 0 to infinity, minus f of t times negative s e to the negative st. And this, well, okay, let's look at this first. At t equals 0, we just get f of 0 times e to the 0, and that's our lower limits. That's going to be negative f of 0. At infinity, we get e to the negative st as t approaches infinity, approaching 0, so we get 0 as we approach infinity. And then over here, this integral is easily simplified. We just factor out the negative s. We get plus s times the integral from 0 to infinity of f of t dt, f of t e to the negative st dt. And what's that? That's just the Laplace transform of f of t, which is our big F of s. So that simplifying this, we get s times big F of s minus f of 0, and now we have a function for the Laplace transform of the derivative of our f of t function in terms of f of 0.